the things, the tissue values that we're counting will pretty much always be, well, most of the time, be traces of adjoints. So the operators we look at are things like traces that have some, A sub m's and A sub SMU news, and ties and so on. But I'm going to make a convention for my lectures. I don't think it's a standard, but as long as I tell you what my convention is, you're ahead of the game. That when I talk about the operator, I'm going to put an N in there. And that way they scale the same way as the vertices. So something like this would look like a vertex, 3 fields, and the trace, connects your indices in this way, and then there's an N just as there is for a vertex. And so with this counting, any Feynman graph, goes as N to the number of vertices, where vertices include these operators on an equal footing, plus loops minus propagators, which, as Phillips remarkably noted, is just the Euler number of the graph when you fill in the index loops. And so you get a topological expansion based on the topology of the graph. So just for the 1 point, so if I have a single, suppose I just have a single phi squared operator. So here's the operator, 2 fields. The simplest graph would be just connect the 2 fields this way, and there's 2 n's from the index loops, an n from the vertex here, the operator, and 1 over the propagators that goes n squared. And indeed, this is when you fill in this index loop, and this index loop is topologically a sphere, which I know is number 2. For a 2-point function, you can do 2 things. So again, and if you dress this up with more propagators, you can do the counting for as many examples as you want. But the argument tells you that you'll always get n squared for anything like that. With 2 operators, there's 2 things you can do. You can either have the disconnected graph, of which this would be the simplest, or you can have the connected graph. And when you fill in the index loop, this is 2 spheres, 2 disconnected spheres, which gives you n to the 4th. This is a single sphere, which gives you n squared. And the general rule with the conventions I've adopted is that so this is connected, the connected expectation value of any number of invariant operators will always scale as n squared, because it's always the leading contribution. The leading spherical, also known as planar if you flatten the sphere out, the leading spherical contribution to any correlator, any number of these invariant operators will scale as n squared. But the largest term will always be the most disconnected one, the product of the 1-point functions. Okay, so that's the lightning summary of the field theory side of this particular duality. So now, the main subject, of course, is to bring these 2 sides together. First, the parameters. Again, let me just. One more thing I should say. The field theory, of course, the reason it plays such a role is that it's conformally invariant, it's scale invariant. If you just write out the beta function, the 1-loop beta function, from this collection of fields, the matter exactly cancels the gauge field. The 1-loop beta function vanishes, and in fact, the beta function vanishes to Eulers and even non-perturbatively. There's a simple Steinbergian argument for that, which I'll give you actually later on when it's more convenient to. So the theory has the implicit symmetry, the Lorentz symmetries, it has the translation variance, and it has scale variance, and the rest of it is formal. Okay, so first parameters, we've already noticed, I think earlier on, that on the ADS side and the CSP side, we have N and N, and we have GA mil squared, and we have G string. Although it might be, okay, there's another way to characterize this on the ADS side, which is if you go back through the definitions, the ratio of the ADS scale to the string scale, where the string scale is just the square root of alpha prime, is just exactly lambda, so c squared n. And the ratio of the ADS scale to the plus scale is essentially n. There's a number here that depends on your convention for what the plus scale is, but it's essentially n. So, coming back to the n-way determination, we need many fields, and we need strong coupling. And strong coupling, again, not just means of order 1, it means much bigger than 1, so that the strings are much smaller than the ADS space, and we can use supergravity. And similarly, this has to be much larger than 1, so that quantum gravity loops are small. And the duality should still be true in the case this is of order 1, and the ADS scale is more of the string scale. We should be able to use some clever solvable string background to talk about this, but there are partly because of the Ramon field to come up with a lot of examples. There's not a lot that's been said about examples of this, but this is order 1. Okay, so there's the meshing of parameters, and the symmetries, again, SO42 cross SO6, the obvious geometric symmetries on the ADS side and on the CFT side. We've just seen this one, and we talked about how the various pieces of the conformal group of the Poincare coordinate fits into that. So those symmetries are the same. There's also the supersymmetries which are the same, so this whole thing fits into a supergroup that I'm not going to try to describe. There are actually 32 of them. There are the 16 that we just talked about up above, and there are 16 superconformal. There's another symmetry which may not come up again, but it's worth remembering that it's there. It's a symmetry, which is there's the SL2R on both sides. This is the weak-strong. So in the 2B string theory, this includes the weak-strong duality, the string duality, and also shifts of the Ramon scalar, discrete shifts. And in the CFT, again, it's the weak-strong. This weak-strong duality of the 2B theory descends to the gauge theory, to the discrete range, and again, it's weak-strong and shifts to the discrete shifts. So the theta parameter. I mean Z, thank you. Discrete shifts for theta parameter. It's too early in the morning. Okay. So the next thing is to talk about the matching of the states. On the ADS side and the states on the CFT side, but we know from general principles of ADS CFT that we can also these are isomorphic to the operators of the CFT, and so the dictionary is more concisely stated in terms of the operators, the local operators of the CFT and ADS states. In particular, again, the single trace operators. So I could have also written something that had quadratic for traces, but I didn't. So the single trace operators map to the one particle states. And that is kind of obvious from the point of view of this statement about how connected amplitudes are smaller, namely in the large n limit. In the large n limit on the CFT side, things factorize as much as possible into single phase into trace operators. On the ADS side, that same limit is turning off the bulk coupling constants, and so you have weakly coupled particles. So if I wanted to count the states, I would probably actually want to do it in the global picture because there I get a discrete spectrum and it's easier to count. So if I wanted to sort of phrase it in this way, I would go to the global picture where ADS is roughly speaking a cylinder. ADS is, as Tisa put it, the soup, and the CFT is sort of the can, it's the boundary, the three-sphere on the outside, and then quantize on the three-sphere, which is isomorphic to these operators, and then compare it to the states here. And in fact, I put in the notes, I guess by tomorrow I'll try to give you an updated note. I put in the notes one small exercise to in fact do a calculation in this language rather than directly. But I'm going to simply use this as motivation to make the statement that the dictionary in the end is between the particles. So it's between the different kinds of single phase operators and the particle species in ADS5. And you can state it in terms of not the particles themselves, but the field operators. So you have some field. I'll keep writing scalar fields just because they're simplest. And again, as we just discussed last time, we're going to quantize these in such a way that the quantum fluctuations, the exponential field, behaves as z to the delta near the boundary, where delta is one of the two roots of m squared equals delta minus d. And we have some freedom as to which route we take in some cases. But whichever route we take, the quantum part of the field has some definite fallout at the boundary. And so if we And if you think about it, if you come back to the original hand-waving interpretation of the z-coordinate, in terms of the size of the state you're making, a local operator, at the point, is creating whatever it creates all on top of each other. It's creating some state of zero size, and so in terms of the dual picture, it should be creating something at z equals 0, as it is. This identity also sort of suggests, like we always think in terms of the CFT living on the boundary of the ADS space. So if the ADS space is the global space, the CFT again is this 3-sphere times time. If it's the Poincare space, which just Eva Silverstein draws it something like this, then this is a Poincare slice, and this is the throat conveying the fact that these directions are shrinking down as you go down to this is the boundary, this is the horizon. The CFT, the local operators of the CFT live here on the boundary of the space. I'm not sure, it's weird because, in a sense, I mean, remember, this is isomorphism of two theories. The CFT, the CFT is the entire gravity theory. It's a complete isomorphism of this theory and this theory. It's not, so it doesn't sort of live just on the boundary, but all of the local observables and pretty much all the observables that we know how to write down live at the boundary. So it's sort of, in a sense, the CFT lives in the boundary of the space, but you have to remember that it really is constructing the entire theory in the interior. It may also bother you when you start to think about it that when we derive this in the Brady construction, all of the d-branes were sitting down here at r equals 0, the horizon. And somehow they've migrated out to here, the other end. And one way to think about this is that these are, again, their positions are quantized. They're fluctuating all the time. And roughly speaking, it's the quantum fluctuations of the original D3 branes that you put in the origin are really building the entire space. And in fact, if you have a scalar field with like the position of a D-brane, and you try to measure it very precisely, you measure it very quickly over a very small volume, you know by principles of quantum field theory that it will fluctuate over an arbitrary long distance. And so as you make more and more local observations on the D3 brane, you're actually going to see things that are further and further away from where you thought they were. So in some sense, you can imagine how the quantum fluctuations of the D3 branes build the whole space. Okay, so we can check real quickly that with this dictionary, the conformal symmetries match up on the two sides. And again, in the CFT there is some list of operators. In the gravity theory, this again is all in 5 dimensions now. You have the 5-sphere. When we did the hand-waving derivation, didn't know that we were also going to find a 5-sphere. I guess we had to because we had to get string theory. But it's different from the ADS directions because the Poincare directions are blowing up as you go to infinity. They feel the warping, and so they have this special kinetic properties. The 5-sphere just remains at some constant size as you move out. It doesn't warp in this way, and so in some sense you can just reduce the harmonics in the 5-sphere and think of these as just different fields in 5 dimensions. So we can check that this dictionary has the correct conformal properties, that this delta that appeared in the solution to the Klein-Gordon equation really is the scaling dimension of the operator. So the scale symmetry, in terms of the Klein-Gordon fields, they're just scalars. The scale symmetry is just a symmetry of space-time. It just moves the points. Just question. Well, it's geometrically, the space that the CFT lives on is the same as the boundary of the ADS space. And again, that shows up very directly in the statement that the local operators in the CFT relate to the boundary limits of the fields. But then I was also saying, but we've got to remember the CFT is dual to the whole space. So, it's not a sharp point I'm making. It's well, again, the branes, in the classical solution, the branes run the other side, but if you actually sort of try to quantify how much they would fluctuate as a quantum object, it's essentially just enough to build the ADS space. So they're everywhere. So equal zeros, we need to take, two reasons. One is, in a theory of quantum gravity, it's very hard to make sharp observables. And the boundary conditions are such that the larger component of the Klein-Gordon field, or for the metric, the larger component of the metric, is fixed at the boundary. And so at the boundaries, it's hard to pin down the metric. But because of this work factor, the metric behaves in some sense more and more classically as you go out to the boundary. And so at the boundary, you have a place where you can sit and define precise observables. So in some sense, the boundary is the natural place to define observables in this theory. And it also interpretation of what Z is. If you could, well, if you tried to make an operator that created a particle somewhere in the middle of ADS space, which lots of people have tried to do, you can do it in free field theory, just using the symmetry. So if you try to make an operator, you run into all sorts of complications and problems, and it's not clear what the precise thing is that you're trying to do, because you don't have local operators in general relativity. You can't, in some sense, create something that has energy at a point in your gravitating theory, because you have to also create its effect on the gravitational field.
Yes, so I'm just trying to understand the statement about single trace operators for functional particle states.
Yeah.
So inherently, if you can trace them from 5 to 5, you get something of the same free field theory. You'll have a whole dagger times a dagger times a dagger. Would you think that somehow in the large interval, only the ones with a single dagger acting in the dagger are
No, I did not. No, sorry, I did not say that. I didn't say that. I said if the single particles in the single particle states in the gravity picture map to the single trace operator. So again, this is the generating picture. The entire cloud of things that this operator creates is a single particle on this side. A multi-trace operator is two particles. A multi-trace operator is two particles. And again, one way to see that in some sense is that discounting tells you that the leading order has two pieces that don't communicate with each other. I don't know if there's a cleaner way. There must be a cleaner way to say it, but if you act with a multi-trace operator, the leading order is going to act like you've just acted with a single trace operator twice, and so it acts like a two-particle state.
Could you comment on whether there's a similar classification of operators for M theory versions?
Good question. Good. So for M theory, now, it's a really good question. Right. So just to expand on, there are, as we go around the landscape of string theory, we get to theories that don't have strings, like M theory, as strong coupling, and there are ADS-CFT duals involving M theory. And in those duals, the CFT side doesn't have a nice planar extension like this, and you get funny and non-Cooktean powers of n. Now, you've thought about this more than I have. So, yeah, you have the obvious harmonics on this. I mean, you have the graviton, you have the obvious supergravity states, and then you have black holes. I mean, think of what do you think about this offline? I don't have anything new to say. So, I mean, but it's true. The fact that there are these two scales, the string scale and the Planck scale, is special to string vacua, and it's sort of special to the fact that this field theory has a coupling that you can tune. Whereas in some sense, the dual to M theory is stuck at lambda equals infinity. It's stuck at, and so, it's sort of the same story but less, at least in terms of the parameters. And in terms of the operators, that's a good question. Does this theory have operators that create black hole states? It does, right? We're not going to talk. Right. Yeah. We're not talking about that. Okay. Oh, good. There should be. Do they have to be stable? I mean, we don't. So we sort of kind of string. Half figure. Well, they have many individuals. They have many individual states.
You want to hear on the sort of tentative answer. If you look from the free field theory point of view, you want to states that you can't thoroughly like black holes do. You have to look at the particle spectrums, scale where you can square.
Okay, good deal.
Way up there, the degeneracy is
right.
And so the first order perturbation theory.
Very good. Good. So large numbers, very large numbers of fields in the trace where the n counting begins to look non-standard. Right, very good. Okay, good. So if you just take the way a scale transformation acts on a scalar field in the bulk and you plug it into that dictionary, you find that this takes O of x to when z goes to 0, z to the minus delta, phi of lambda z and x, which by renaming the dummy index v is lambda to the delta, then z to the minus delta, phi of z and x, which is lambda to the delta, O of and x. So in this middle step, we've taken z over lambda, just as a dummy index. And so indeed, the operators defined in this way scale as they should under scale transformations. And in particular, the exponent that we got from the limiting behavior of the Klein-Gordon equation really is the dimension of the corresponding operator. Okay. By the way, these scalings, later on I'll do one calculation with gravitons, but these scalings work the same way. I think this is always true if you refer things to tangent space indices. So